Welcome to today's paper reading. Today's paper is titled, Does Fine-Tuning LLMs on New Knowledge Encourage Hallucinations? This paper was published on the AR14 preprint by Zorik, Gekhman, and colleagues from Technion Israel Institute of Technology and Google Research. In this study, the authors investigate the effects of supervised fine-tuning on large language models when they are exposed to new factual information not covered in pre-training. They hypothesize that this exposure can lead to the model generating factually incorrect responses, or hallucinations, as it is trained to produce facts not grounded in its existing knowledge. To explore this, they design a controlled experiment focusing on closed-book question answering, where they manipulate the proportion of fine-tuning examples that introduce new knowledge. The results show that while large language models struggle to learn new facts through fine-tuning, they eventually do, and this learning correlates with an increased tendency to hallucinate. These findings underscore the risks associated with introducing new factual knowledge through fine-tuning and suggest that models primarily acquire factual knowledge during pre-training, with fine-tuning enhancing their ability to use this knowledge more effectively. In this study, we explore the effects of fine-tuning on large language models, LLMs. Pre-training on large textual corpora embeds substantial factual knowledge into the model's parameters, which is crucial for various downstream applications. However, these models often need further alignment to desired behaviors, typically achieved through supervised fine-tuning on instruction-following tasks and preference learning from human feedback. During fine-tuning, the model may encounter new factual information, raising questions about how LLMs integrate this new knowledge. We propose SLIC, a hierarchy of knowledge categories to assess the consistency of fine-tuning examples with the model's knowledge. Our controlled study focuses on closed-book question answering, varying the proportion of unknown fine-tuning examples to observe their impact on the model's tendency to hallucinate. We also examine the effects of early stopping and filtering out unknown examples to mitigate overfitting. Figure 1 illustrates the training and development accuracies over the duration of fine-tuning, specifically when the fine-tuning dataset consists of 50% known and 50% unknown examples. The key observation is that unknown examples are significantly slower to fit compared to known examples. The peak development performance is achieved when the large language model, LLM, has fitted the majority of the known training examples, but only a small fraction of the unknown ones. Beyond this point, the fitting of additional unknown examples leads to a decline in performance, indicating a potential negative impact on the model's effectiveness. In this study, the dataset D is constructed to reflect instruction tuning on diverse knowledge-intensive tasks. The factual knowledge is structured as subject, relation, object, triplets and converted into closed-book QA format. To study the effect of new knowledge on the model's performance, variants of D are created with varying proportions of examples unknown to the pre-trained model M. The entity questions dataset is used, focusing on 12 diverse relations and reserving 7 for an out-of-distribution test. The POM2S base model is employed, with exact match, EM, as the evaluation metric. Full technical details are provided in A. Figure 2 illustrates the formal definitions of the SLIC knowledge categories, which are derived from the P-correct measure. These categories help in understanding the model's knowledge levels. Highly known examples are those where the model always predicts the correct answer greedily. Maybe known examples are those where the model sometimes predicts the correct answer greedily. Weakly known examples are those where the model never predicts the correct answer greedily but can predict correctly with temperature sampling. The figure also provides real examples from the entity questions dataset to demonstrate these categories. To evaluate the impact of new knowledge on the performance of a model, we need to annotate each question-answer pair in the dataset with respect to whether the model knows the correct answer. This is done by defining a continuous measure called P-correct, which estimates the likelihood of the model generating the correct answer. We use this measure to categorize each pair into 4 knowledge categories. The definition of P-correct considers whether the model, when prompted with few-shot exemplars, generates the correct answer. Due to the randomness introduced by temperature sampling, P-correct reflects the variability in the model's predictions. Based on P-correct, we categorize pairs as unknown if the model never predicts the correct answer, and known if it sometimes does. Known pairs are further divided into highly known, maybe known, and weakly known based on the consistency of the model's greedy predictions. Figure 3 illustrates the impact of the percentage of unknown examples in the fine-tuning dataset D on test performance. In Part A, the graph shows performance for different fixed numbers of epochs, with early_stop indicating the epoch where early stopping is applied based on the development set. Performance degrades as the percentage of unknown examples increases, regardless of the fine-tuning duration. Early_stop generally yields the best performance, while longer training durations often result in overfitting, especially with higher percentages of unknown examples. In Part B, the ablation study shows that filtering out unknown examples, D-known, results in similar performance to D for early_stop, indicating a neutral effect of unknown examples. However, for longer training durations, the presence of unknown examples significantly increases the risk of overfitting. In this section, we explore the impact of unknown examples in the fine-tuning dataset on model performance. We observe that a higher percentage of unknown examples leads to performance degradation, regardless of the fine-tuning duration. Specifically, early stopping, early_stop, typically yields the best performance, while training for more epochs, especially with a higher percentage of unknown examples, increases the risk of overfitting. To further investigate, we use a linear regression model to assess the relationship between the type of training examples and test accuracy. The model indicates that fitting unknown examples negatively impacts performance, while fitting known examples improves it. This suggests that unknown examples, while not necessarily harmful in the early stages, become detrimental when the model is allowed to converge, highlighting the importance of careful dataset composition and training strategies. Table 1 presents the results of our linear model for predicting the test accuracy as defined by equation 1. The model coefficients beta0, UNC, and beta-kn are estimated to understand the impact of fitting known and unknown training examples on test accuracy. The high R2 values indicate a strong linear relationship between test accuracy and the type of training examples that are fitted. Specifically, fitting unknown examples, UNC, negatively impacts performance, while fitting known examples, beta-kn, improves it. The estimated negative impact from unknown roughly matches the positive impact from known, suggesting a balanced effect. This linear model is crucial for assessing the proportional influence of different types of training examples on the model's test performance. Figure 4 illustrates the state of the examples in the fine-tuning dataset D after the early_stop point. Each variant of D is represented on the y-axis, showing the portion of examples in D that the model has fitted, meaning it predicts the correct answer for Q. This visualization helps to understand the model's performance and fitting behavior across different dataset variants. Table 2 presents the accuracies for single-category variants of the fine-tuning dataset D, evaluated across different subsets of the test set. The variants include D highly known, D maybe known, D weakly known, D unknown, and D natural. The table shows that D maybe known achieves the best overall performance, excelling particularly on maybe known test examples. In contrast, D highly known performs well on highly known test examples but shows inferior performance on other categories. The results indicate that unknown examples have a neutral effect on performance, as their removal has minimal impact. This suggests that maybe known fine-tuning examples are essential for the model to handle such examples during inference, enhancing its capability to utilize pre-existing knowledge. To investigate the impact of different knowledge categories on model performance, we created specialized datasets for each category. These datasets, denoted as DCAT, allowed us to analyze how training with examples from specific categories affects test performance. Additionally, we included a natural distribution dataset, D-natural, for comparison. Our findings, presented in Table 2, show that while training on highly known examples, D highly known, performs well on highly known test examples, it underperforms on other categories. In contrast, D maybe known achieves the best overall performance, suggesting that maybe known examples are crucial for handling such examples during inference. Furthermore, our analysis in Section 4.2 revealed that unknown and weakly known examples increase the risk of overfitting. This was evident when comparing performance at convergence and early_stop, where D weakly known and D unknown showed significant drops. Interestingly, D natural performs similarly to D may be known at early stop but degrades significantly after convergence, indicating overfitting issues likely due to the presence of weakly known and unknown examples. These results collectively highlight D may be known's superior performance and reduce risk of overfitting. In this section, we delve into the slick knowledge categories analysis. Firstly, we discuss the fine-grained categorization of known facts, which includes highly known, may be known, and weakly known. The highly known category consistently achieves over 95% accuracy, indicating a high degree of knowledge. Conversely, may be known and weakly known represent weaker knowledge states, with performance on weakly known being worse than may be known but better than unknown. Secondly, we benchmark the unknown test examples, where the model's accuracy is extremely low, suggesting that these examples are truly unknown to the model. Lastly, we compare our approach with the p-true method, which estimates the probability of correctness. Our results show that our approach categorizes unknown examples more effectively, leading to significantly worse performance post-fine-tuning compared to the p-true based method. Additionally, the use of multiple few-shot prompts is crucial for approximating p-correct, as fewer prompts lead to higher test accuracy on slick unknown examples. Figure 5 compares the slick unknown categorization with classifying examples as unknown based on a p-true threshold. The x-axis represents the percentage of test examples classified as unknown, while the y-axis shows the accuracy on these examples after fine-tuning. The yellow line indicates the p-true metric for thresholds t ranging from 0 to 1. The blue circle represents our unknown category, and the blue line corresponds to approximating p-correct using fewer than 10 random 4-shot exemplars. In this section, the authors explore methods to mitigate overfitting when fine-tuning models on unknown examples. They discuss 3 primary strategies: early stopping, filtering out unknown examples, and relabeling unknown examples with an uncertainty expression. The experimental results show that while there is a performance drop when comparing D to DIDK, relabeling unknown examples significantly reduces the risk of overfitting. Specifically, the accuracy for DIDK remains stable across different fine-tuning conditions, with a slight decrease in the number of willingly answered questions. These findings suggest that relabeling unknown examples can be an effective strategy to improve model performance and reduce overfitting. This work highlights the risk in using supervised fine-tuning to update large language models' knowledge. Empirical evidence shows that acquiring new knowledge through fine-tuning is correlated with hallucinations regarding pre-existing knowledge. Additionally, the study found that unknown examples are fitted slower than known ones, leading to overfitting. This emphasizes the importance of using early stopping instead of a fixed number of fine-tuning steps. However, early stopping may be less effective when fine-tuning on numerous tasks with distinct, optimal stopping points. An alternative solution is to filter out unknown examples during fine-tuning, which can reduce the risk of overfitting without compromising performance. Relabeling unknown fine-tuning examples with uncertainty expressions, such as I don't know, can also reduce their negative effect. The superficial alignment hypothesis suggests that most of an LLM's knowledge is acquired during pre-training, with fine-tuning learning mainly the style or format for interacting with users. However, this work shows that fine-tuning also significantly influences the model's capability to utilize its pre-existing knowledge, indicating that the model learns more than just style or format through fine-tuning. Table 3 presents the results of fine-tuning with the label of unknown examples replaced with I don't know. The D variant includes 50% known and 50% unknown examples, while the DIDK variant relabels all 50% unknown examples with I don't know. The accuracy is evaluated on the subset of test questions that were answered, meaning the model did not respond with I don't know. In the related work section, several studies have explored the phenomenon of hallucination in large language models, LLMs. Shulman, 2023, Goldberg, 2023, and Gooderband et al., 2023, conjecture that fine-tuning on new factual knowledge may lead to hallucinations. Huang et al., 2023, categorize these causes and define the issue as capability misalignment, emphasizing the challenge of defining the knowledge boundary of LLMs. Recent studies support these findings. For example, Ghoshal et al., 2024, demonstrated that models fine-tuned on well-known facts show improved factuality compared to those fine-tuned on less familiar facts. Lin et al., 2024, found that using data generated by a retrieval-augmented model led to reduced factuality due to the introduction of new factual knowledge. Ren et al., 2024, also investigated the effects of fine-tuning with new factual knowledge, focusing on multiple-choice questions and short fine-tuning runs. Their results align with the findings of this paper. Additionally, Dubé et al., 2024, integrated these insights into the instruction tuning phase of Llama 3 models to ensure alignment with pre-training knowledge. Another line of research examines the model's behavior with new knowledge at test time. Kang et al., 2024, showed that fine-tuned LLMs mimic responses associated with unknown examples when encountering unknown queries. Yin et al., 2023, and Li et al., 2023, also analyzed the impact of new knowledge on LLM performance. Lastly, the quantification of knowledge in LLMs is another area of interest. SLIC is proposed as a confidence elicitation method for ground truth labels. Existing work derives calibrated confidence from LLMs through various methods, such as examining agreement across multiple samples, probing internal representations, eliciting verbalized probabilities, or direct prompting. Kadavath et al., 2022, also trained a separate model to predict if the LLM knows the answer, which is conceptually aligned with the approach in this paper. In this study, the authors investigated the impact of integrating new factual knowledge through fine-tuning on the model's tendency to hallucinate. They introduced SLIC, a categorization of facts relative to the LLM's knowledge, and designed a controlled study to isolate and rigorously evaluate the effects of new knowledge. Key findings include that acquiring new knowledge via supervised fine-tuning is correlated with hallucinations regarding pre-existing knowledge, and that LLMs struggle to integrate new knowledge through fine-tuning, primarily relying on their pre-existing knowledge. The study also acknowledges limitations such as challenges in knowledge integration, biases towards pre-existing knowledge, and the complex dynamics of fine-tuning. The study has several limitations. Firstly, the experiments were conducted using only one large language model, LLM, which raises questions about the generalizability of the results to other LLMs. This choice was partly due to the computationally intensive nature of the fine-tuning process, which required long runs to analyze behavior at different stages, including overfitting. Secondly, the study involved extensive dataset annotation with respect to specific categories, necessitating 170 inference steps per example, totaling over 15 million inference steps. This was crucial for accurately assessing the model's knowledge. Lastly, the focus on closed-book question answering, QA, means that practical implications, such as filtering out unknown fine-tuning examples, need validation in settings involving long-form text generation. This would require adaptations to the evaluation method and is left for future work. In this section, the authors expressed their gratitude to the reviewers for their valuable comments and suggestions, which significantly contributed to the improvement of this work. They also acknowledged the contributions of several individuals, including Ori Ram, Yuri Shaham, Alon Jacobi, Mor Ventura, Yochai Blau, Eyal Ben David, Avi Kassialaru, Avinatan Hasidim, and members of Roee Reichart's NLP group, who reviewed the paper draft and provided essential feedback. Special recognition is given to Yuri Shaham for his assistance in setting up the fine-tuning pipeline during the early stages of the research, which was crucial for the project's development. Thank you for watching.